The universe, in its vast and unending quiet, is not truly empty. It is a canvas of infinite depth, painted with a darkness so absolute that the human mind struggles to comprehend it. We look up from our small blue home and we see the pinpricks of light that we call stars. For thousands of years, these lights were merely static points on a celestial sphere, unmoving, unchanging, silent sentinels of the night. We navigated by them, we told stories about them, we worshipped them, but they remain distant, cold, and unknowable. To the naked eye, the cosmos is a still image. It is a frozen tapestry where nothing seems to happen on a timescale that we can perceive. A star twinkles, but that is merely the turbulence of our own atmosphere, a trick of the air we breathe. Out there in the true void, the stars burn with a steady, unblinking gaze, or so it seemed. But silence is often an illusion. Stillness is often a matter of perspective. If one could drift closer, past the moon, past the orbits of our freezing giants, Neptune and Uranus, and out into the interstellar deep, the silence would begin to change. It would become a hum of energy. The stillness would reveal itself to be a chaotic, beautiful dance of gravity, heat, and light. And now, we have a way to see this dance. We have built an eye capable of piercing the veil of distance. We have constructed a machine of gold and beryllium, a delicate origami flower of mirrors that unfolded in the cold vacuum 1.5 million kilometers from Earth. This is the James Webb Space Telescope. It is our silent watcher. It sits at a gravitationally stable point known as Lagrange point 2, turning its back on the Sun, turning its back on the Earth, and facing the eternal night with a sensitivity that borders on the magical. It was designed to look back to the beginning of time, to catch the faintest, reddest light from the very first galaxies that ignited after the Big Bang. And it has done that. It has shown us the infant universe. But it has also done something else, something perhaps even more profound for our understanding of our place in the cosmos. It has turned its golden gaze upon the stars closer to home, stars within our own galaxy, and looked not at the stars themselves, but at the shadows crossing them. It has looked at the worlds orbiting those stars, the exoplanets. For decades, we knew these planets existed only by the wobble they caused in their parent stars or by the tiny dip in brightness as they passed in front. They were mathematical ghosts. We knew their mass, perhaps their size, but they were featureless. They were data points on a graph. We called them hot Jupiters or super-Earths, giving them names that evoked our own solar system, yet we knew nothing of their true nature. We did not know what it would be like to stand beneath their skies. We did not know if they had skies at all. But the universe is full of surprises for those who wait with patience. Recently, the James Webb Space Telescope trained its sensors on a specific point of light, a distant system light-years away from our Sun. It stared for hours, collecting photons that had traveled across the vast emptiness for centuries. It gathered this light, split it into a rainbow of colors, a spectrum, and looked for the missing pieces. And in that data, hidden in the subtle absorption of infrared light, it found something that changed everything. It did not just find an atmosphere. It did not just find water vapor or carbon dioxide, though those are miraculous discoveries in themselves. It found weather. It detected the movement of air. It detected the swirling of clouds. It detected the dynamic, chaotic, ever-changing churn of a planetary atmosphere on a world that no human eye will ever see directly. It found that this distant world is not a dead rock, nor a static ball of gas. It is a place of activity, a place where the wind blows, a place where clouds form and dissipate, a place where the temperature shifts from day to night, driving storms that wrap around the entire planet. Let us pause and consider the magnitude of this. We are sitting on our own planet, feeling the breeze on our faces, watching the rain fall, accustomed to the idea of weather. It is mundane to us. But to detect the shifting winds on a world hundreds of trillions of miles away, that is a triumph of stillness. It requires us to be so quiet, so precise, and so patient that we can hear the whisper of a storm across the galaxy. This documentary is a journey into that discovery. We will not rush. We will drift slowly through the data, visualizing the invisible. We will float above the cloud tops of this distant world. We will feel the heat of its star and the chill of its night. We will explore what it means to say that a planet is active. First, we must understand the instrument that made this possible. The James Webb is often described by its cost or its engineering complexity, but in the context of this discovery, it is better thought of as a time machine and a chemist combined. Its mirrors are coated in a microscopic layer of gold, chosen because gold is the supreme reflector of infrared light. Infrared is the light of heat. It is the light that penetrates dust. It is the light that reveals the thermal glow of the universe. When we look at a distant planet with visible light, the light our eyes can see, we are often blinded by the glare of the parent star. The star is billions of times brighter than the planet. It is like trying to see a firefly hovering next to a searchlight. But in the infrared, the contrast changes. The planet glows with its own internal heat. The star is still bright, but the planet begins to emerge from the glare. The telescope sits in the absolute cold, protected by a sun shield the size of a tennis court. This shield blocks the heat of the sun and earth, allowing the telescope's instruments to cool down to nearly absolute zero. In this profound cold, the telescope becomes sensitive to the tiniest fluctuations in heat from deep space. It was in this state of supercooled silence that Webb looked at the target. The planet in question is not like Earth. It is a stranger place, a world of extremes. But the physics that govern it are the same physics that govern the trade winds of the Pacific or the hurricanes of the Atlantic. Heat moves from hot areas to cold areas. Energy seeks equilibrium. The discovery was not a single image. There is no photograph of swirling clouds like the famous blue marble photo of Earth. Instead, the discovery came in the form of a light curve, a graph showing the brightness of the planet over time. As the planet rotated, bringing different faces into view, the telescope measured the heat coming from it. If the planet were a stagnant, unmoving rock with no atmosphere, the hottest part would be directly under the star, high noon, and the coldest part would be on the opposite side. The temperature map would be simple, but the data showed something else. The hottest point was shifted. The heat was being dragged away from the noon position. Something was carrying the heat around the planet. That something is wind. Massive, equatorial jets of wind screaming through the upper atmosphere at thousands of miles per hour. These winds are the engines of the planet's weather. They are distributing the energy of the star, mixing the atmosphere, churning the chemicals that float there. And within those winds, the telescope detected the signature of clouds. But these are not clouds of water vapor like the gentle cumulus clouds of a summer day on Earth. These are clouds born of fire and sand. We will journey into the composition of these clouds later. But for now, hold this image in your mind, a world wrapped in ribbons of high-speed wind, carrying clouds made of rock dust, shimmering in the infrared dark, a dynamic marble suspended in the velvet night. This is the era of exoplanet meteorology. We have moved from being stamp collectors, simply counting the planets we find, to being meteorologists, watching the weather forecast of alien worlds. The universe is coming alive. The static map is becoming a motion picture, and we are just beginning to watch the show. To understand how we can see the weather on a world we can never visit, we must first understand the language of light. Light is the only messenger we have. It is the only thread connecting us to the rest of the cosmos. Everything we know about the universe, from the composition of stars to the expansion of space itself, comes from decoding the messages hidden within rays of light. Imagine a beam of starlight as a tightly wound cord. To the naked eye, it appears white or slightly yellow. But if you unravel that cord, if you pass it through a prism or bounce it off a diffraction grating, it splays out into a rainbow. This is the spectrum. Every element in the periodic table, every molecule that exists, leaves a unique fingerprint on this rainbow. Hydrogen absorbs light at specific colors, oxygen at others, water vapor, methane, carbon dioxide. They all subtract specific slivers of light from the spectrum, leaving behind dark bands like a barcode. By reading this barcode, astronomers can determine exactly what a distant object is made of. This technique is called spectroscopy. It is the foundation of modern astrophysics. It is how we know the sun is made of hydrogen and helium without ever sending a probe to sample it. And it is the tool that the James Webb Space Telescope uses with unprecedented precision. When we study an exoplanet, we usually use a method called transit spectroscopy. We wait for the planet to pass in front of its star. As the planet drifts across the stellar disk, a tiny fraction of the starlight passes through the planet's atmosphere on its way to Earth. The atmosphere acts as a filter. If there is water in that atmosphere, the water molecules will absorb the specific wavelengths of light associated with water. When the light reaches Webb's mirrors, those wavelengths will be missing or dimmed. But detecting weather requires something more dynamic than a single snapshot. Weather is, by definition, change. It is the evolution of the atmosphere over time. To see weather, we cannot just look once. We must watch. We must stare. The observation that revealed active weather on this distant world involved a technique known as phase curve monitoring. This is a patient, meditative process. The telescope locks onto the star system and stays there. It does not blink. It keeps its shutters open, drinking in the light as the planet completes a full orbit around its star. Most of the planets we study in this detail are tidally locked. This means the same side of the planet always faces the star, just as the same side of the moon always faces the Earth. One side of the planet is locked in eternal day, baked by the relentless radiation of its sun. The other side is locked in eternal night, facing the frozen void. On a world without an atmosphere, the temperature difference between the day side and the night side would be catastrophic and absolute. The day side would be molten, the night side would be near absolute zero. The transition line, the terminator, would be a sharp boundary between fire and ice. But an atmosphere changes this equation. An atmosphere is a fluid. It wraps the planet in a blanket of gas. When the day side heats up, the gas expands. It creates high pressure. On the night side, the gas cools and contracts, creating a vacuum that pulls the air toward it. The universe abhors a difference in pressure. And so, the air moves. It rushes from the hot side to the cold side, creating wind. This global wind acts as a conveyor belt for heat. It scoops up the thermal energy from the day side and carries it around to the night side, warming the darkness. As the James Webb Space Telescope watched the planet rotate, it measured the total infrared light coming from the system. When the planet's eternal day side was facing the telescope, the brightness was at its peak. When the night side turned toward the telescope, the brightness dipped. By carefully mapping this rise and fall of light, astronomers constructed a map of the planet's surface temperature. And this is where the magic lies. They found that the heat was not evenly distributed. The atmosphere was doing work. It was churning. But there was more. The data showed distinct signatures of clouds, and not just a uniform haze, but patchy, broken clouds that moved and evolved. On Earth, clouds are transient. They form, they rain, they vanish. They block the sunlight, cooling the ground beneath them. They trap heat, warming the air below them. They are the visible expression of the atmosphere's mood. On this distant world, the clouds play a similar role, but their composition is alien to our experience. The data suggests that these clouds are not made of water. The planet is too hot for liquid water clouds to exist in the upper atmosphere. Instead, the chemistry points to silicates. Rock. Sand. Imagine a cloud made of microscopic grains of sand. Imagine a mist of quartz. In the intense heat of the atmosphere, rock vaporizes. It becomes a gas. As this hot gas rises and moves toward cooler regions, perhaps pushed by those supersonic winds toward the night side, it cools and condenses. Just as water vapor condenses into droplets of liquid water on Earth, vaporized rock condenses into tiny crystals of sand on this world. So, the weather forecast for this distant planet involves swirling storms of silicate dust. The clouds are glittering, reflective veils of minerals. They form in the twilight zones, or perhaps they cloak the night side, trapping the heat inside. They are heavy clouds, dense and opaque. The telescope observed that the brightness of the planet fluctuated in ways that could not be explained by rotation alone. The brightness flickered. This variability is the telltale sign of active weather. It means that the cloud cover is changing. At one moment, the telescope might be looking at a clear patch of atmosphere, seeing deep down into the hotter layers. An hour later, a massive bank of silicate clouds might roll in, obscuring the view and changing the infrared signature. This variability confirms that the atmosphere is turbulent. It is not a stagnant pool, it is a roiling ocean of gas. There are updrafts lifting the silicate vapor. There are downdrafts where the sand rains out, perhaps falling into the deeper, hotter layers where it turns back into magma vapor. The concept of sand rain is difficult to visualize, but it is physically real. On Earth, the cycle is evaporation, condensation, precipitation. Water becomes vapor, vapor becomes cloud, cloud becomes rain. On this exoplanet, the cycle is the same, but the material is rock. Rock becomes vapor, vapor becomes sand cloud becomes sand rain. The James Webb Space Telescope has allowed us to witness this cycle. It has allowed us to peer into the cauldron of an alien sky and say, with certainty, the wind is blowing there today. It connects us to that world in a way that static data never could. Weather is something we feel. We understand the changing sky. To know that a world light years away has a changing sky makes it real. It transforms it from an astronomical object into a place with mornings and evenings, though they are fixed in space. A place with storms that may rage for centuries or dissipate in hours. A place where the light of a foreign star filters through clouds of diamond dust and quartz, casting strange shadows on a landscape of gas and pressure. We are just scratching the surface of what this means. The ability to detect weather is the first step toward understanding the climate of exoplanets. And climate is the long-term story of a world. It is the story of habitability. While this specific world may be too hot for life as we know it, the techniques used to find its weather are the same techniques we will use to find weather on smaller, cooler, rocky worlds. We are practicing. We are learning to read the clouds of giants so that one day we might read the clouds of a second Earth. We are honing our ability to see the subtle shifts in light that betray the presence of a storm, a season, a cycle. But for now, let us simply rest in the wonder of the achievement. A telescope floating in the silence behind the moon has felt the heat of a sandy wind blowing on a world billions of miles away. The universe is speaking to us, whispering its secrets in the language of infrared light. And for the first time in history, we have the ears, or rather, the golden eye, to listen. The darkness is not empty. It is full of wind. It is full of clouds. It is full of worlds that are breathing, moving, and evolving in the dark. To understand the weather on a world light years away, we must first let go of our earthly intuition. When we speak of weather, we think of the gentle patterns of our own lives. We think of the morning mist rising from a river, the gathering of grey clouds before a summer storm, or the seasonal shift from the warmth of autumn to the chill of winter. Our weather is driven by the rotation of our planet, the tilt of our axis, and the heating of our oceans. It is a cycle of water and sun, a rhythmic breathing of the earth that we have known since our species first looked up at the sky. But the world, the James Webb Space Telescope has observed, operates on a different set of rules. It is a world of extremes, a place where the concepts of day and night are not measurements of time, but permanent locations in space. This planet is tidally locked to its star. This means that its rotation is perfectly synchronized with its orbit. It takes exactly as long to spin once on its axis as it does to travel once around its sun. The result is a world of permanent duality. One half of the planet faces the star forever. It is a land of eternal noon, where the sun hangs motionless in the sky, a searing eye that never blinks, never sets, and never softens its gaze. The other half of the planet faces the void. It is a land of eternal midnight, a hemisphere of darkness that has never known the warmth of the sunrise. Between these two halves lies the Terminator line, a twilight zone of perpetual dusk and dawn. Here, the star sits forever on the horizon, casting long, unmoving shadows across a landscape that exists in a state of suspended animation. If this planet were a solid rock like the Moon or Mercury, the story would end there. The day side would bake, the night side would freeze, and the silence would be absolute. But this planet is not rock. It is a giant of gas and gravity wrapped in a thick, turbulent atmosphere. And an atmosphere, by its very nature, refuses to sit still. Gas is a fluid. When you heat a fluid in one place and cool it in another, it moves, it seeks equilibrium. The immense heat of the eternal day side causes the atmosphere to expand, to rise, to push outward with tremendous pressure. On the night side, the gas cools and contracts, creating a vacuum that pulls the air toward it. This pressure difference creates wind, but not wind as we know it. These are not the breezes that rustle leaves. These are planetary jets, rivers of air that scream through the upper atmosphere at thousands of miles per hour. They are global superstorms that wrap around the entire equator of the planet. The James Webb Telescope detected this movement through the delicate measurement of heat. As the telescope observed the planet, it noticed a strange anomaly. On a stationary world, the hottest point, the hotspot, should be directly beneath the star at the point of high noon. This is where the stellar radiation is most intense. It is the geometric center of the day side. But the data from Webb showed that the hotspot was not there. It had drifted. The point of maximum heat was shifted to the east, dragged away from the noon position. There is only one force in the universe capable of moving the hottest part of a planet's atmosphere away from the heat source: wind. Imagine the scale of this. The atmosphere is absorbing the colossal energy of a star, heating up to thousands of degrees, and before it can radiate that heat back into space, a jet stream catches it. The wind is so fast, so powerful, that it physically carries the heat energy around the curve of the planet, dragging the thermal signature of noon into the afternoon and pushing it toward the night. This is a phenomenon known as superrotation. The atmosphere is moving faster than the planet itself is spinning. It is a global conveyor belt of energy, a ceaseless redistribution of heat that prevents the day side from boiling off completely and keeps the night side from freezing into a solid block of ice. We are looking at a planetary engine. The star provides the fuel, the raw heat, the atmosphere provides the machinery, the expanding and contracting gas, and the result is a perpetual storm that has likely been raging for billions of years. From the vantage point of space, if we could see with infrared eyes, this wind would look like a glowing band of energy wrapped around the planet's equator. It would be brighter on the day side, fading into a dull red glow as it crosses the Terminator into the night. It is a river of fire flowing through the dark. Inside this wind, the conditions are ferocious, yet there is a mathematical beauty to the flow. The air is not moving chaotically, it is stratified, organized into layers of speed and temperature. Deep down, in the crushing depths of the planetary interior, the air might be sluggish, thick and hot. But up high, where the atmosphere thins out into the vacuum of space, the winds race unchecked. The discovery of this wind by the James Webb Telescope is a triumph of deduction. We cannot see the wind directly. We cannot see the clouds moving in real time like we can on a weather satellite map of Earth. The planet is too far away, a mere point of light even to our most powerful eyes. We see the wind only by its shadow, by the footprint it leaves on the temperature map. We see the consequence of the wind. This tells us that the atmosphere is efficient. It is doing exactly what physics demands of it. It is taking the stress of the tidal lock, the extreme heating of one side, and solving it through motion. The planet is healing itself of the temperature imbalance through the mechanism of weather. But what happens when this superheated air, carrying the thermal memory of the star, rushes into the cold of the eternal night? This is where the weather becomes truly alien. This is where the chemistry of the cosmos begins to paint pictures that defy our terrestrial imagination. As the wind crosses the terminator line, leaving the permanent sunshine and entering the permanent dark, the temperature begins to drop. It does not drop instantly. The wind carries the heat deep into the night side. But eventually the cooling wins. The gas begins to lose its energy. The molecules slow down. On Earth, when warm, moist air cools down, water vapor condenses into clouds. We see this every time we breathe out on a cold day. The invisible gas becomes visible droplets. On this distant world, the same process occurs, but the ingredients are different. There is no water vapor here, or at least not in the way we know it. The air is too hot for water to condense. The clouds that form in this cooling wind are not made of ice or liquid droplets. They are made of rock. The James Webb Telescope has detected the spectral signature of silicates in the atmosphere. Silicates are the family of minerals that make up the vast majority of rocks on Earth. Quartz, feldspar, olivine. The sand on our beaches, the granite in our mountains, the glass in our windows. These are silicates. On this exoplanet, the heat is so intense on the day side that rock does not exist as a solid. It exists as a vapor. Imagine a volcano that erupts not with lava, but with gas. Now imagine that the entire atmosphere is filled with this gas. Gaseous magnesium, gaseous iron, gaseous silicon dioxide. It is transparent, invisible, just a hot, heavy part of the air. But as the wind carries this rock vapor into the cooler regions, either toward the night side or perhaps up into the higher, colder layers of the atmosphere, it reaches a critical point. It hits its dew point. Just as water vapor turns to dew on a cool morning grass, the rock vapor on this planet turns to dust. It condenses. Atoms of silicon and oxygen snap together, locking into crystal structures. They form microscopic grains of sand. They form tiny shards of glass, and so the clouds appear. This is the second great revelation of the Webb observations. We are not just seeing wind, we are seeing the formation of solid matter from the air. We are seeing the birth of dust. Let us drift now into the heart of the anomaly. Let us descend from the high, thin vacuum of space and enter the upper atmosphere of this distant world. We are no longer observing from the safety of the Lagrange point. In our minds, we are there, suspended in the roiling currents of an alien sky. The environment here is a paradox of beauty and violence. The light is strange, a glowing reddish-orange hue, born of a star that is cooler and redder than our sun, filtered through layers of haze. The heat is oppressive, a physical weight that presses against everything. But it is the clouds that command our attention. On Earth, clouds are soft. They are made of water droplets or ice crystals, ephemeral and light. If you fly through them in an airplane, they are a white fog. They dampen sound. They scatter light. On this world, the clouds are made of stone. The James Webb Space Telescope, through its meticulous dissection of infrared light, found the fingerprint of silicate particles. Specifically, it found signatures that match minerals like enstatite and forsterite. These are magnesium silicates. On Earth, you might find them in the green sands of Hawaii or deep within the mantle of our planet. They are hard, solid rocks. But here, they hang in the sky. The process begins in the deep, hot layers of the atmosphere. Down there, the pressure is immense, and the temperature soars well above the melting point of rock, above 2,000 or 3,000 degrees. In this inferno, rocks are not solid. They are not even liquid magma. They are vapor. Individual molecules of magnesium, silicon, and oxygen float freely, mixed with hydrogen and helium. They are invisible constituents of the air, just as nitrogen and oxygen are invisible to us on Earth. But the atmosphere is not static. Convection currents, massive bubbles of hot gas rise from the depths. They are like thermal columns in a desert, but on a planetary scale. These updrafts carry the rock vapor upward, higher and higher, toward the edge of space. As the gas rises, it expands and cools. This is a universal law of thermodynamics. The higher you go, the colder it gets. Eventually, the rising gas hits a specific temperature boundary. It is the condensation point for silicates. Suddenly, the rock vapor can no longer stay gaseous. The energy that kept the molecules apart is gone. The electromagnetic forces take over, snapping the atoms together into rigid lattices. In an instant, the invisible becomes visible. A cloud is born. But these are not the fluffy white clouds of a gentle afternoon. These are clouds of glittering dust. They are composed of trillions of microscopic grains of sand and glass. Because they are made of rock, they interact with light differently than water clouds do. They might appear yellowish, or perhaps a smoky grey, or even reflective like crushed diamonds, depending on the size of the grains and the angle of the star. Imagine a towering cumulonimbus cloud, but instead of water vapor, it is a billowing mountain of hot sand. It rises 10 miles high, churning and rotating, fed by the heat below. Inside the cloud, the particles collide. They might grow larger, clumping together from microscopic dust into larger grains, perhaps the size of beach sand or even small pebbles. And then, just as on Earth, gravity asserts its claim. The particles become too heavy to be supported by the updrafts. They begin to fall. This is the precipitation of a gas giant. It rains rock. But the rain never hits the ground, for there is no ground to hit. This is a planet without a surface. It is gas all the way down to a metallic core buried under millions of atmospheres of pressure. So, the sand falls. It rains down through the cloud layers, a shower of silicate crystals plummeting into the deepening gloom. As it falls, it re-enters the hotter, denser layers of the atmosphere below. The temperature rises, the heat attacks the crystals, the lattice vibrates, weakens, and finally breaks. The sand evaporates. The rock turns back into gas. The rain creates its own end, sublimating into vapor before it can reach the depths. This vapor is then caught by the deep winds, cycled back around, and eventually lifted up again to form new clouds. It is a closed loop, a cycle of eternal creation and destruction. Vapor to dust, dust to rain, rain to vapor. The James Webb Space Telescope detected this cycle by looking at the fuzziness of the planet's spectrum. When astronomers analyzed the light, they found that the features of water and other gases were muted. They were not as sharp as they should be if the atmosphere were clear. Something was blocking the view. Something was scattering the light, acting as a haze. That haze is the cloud deck. By measuring exactly how the light was blocked at different wavelengths, the telescope could determine the size of the particles. It turns out they are small, sub-micron in size. Think of smoke particles or very fine flour. This tells us that the clouds are likely high in the atmosphere, a thin, misty veil of silicates rather than a solid wall of rock. But the most remarkable thing Webb found was the change. In previous observations of exoplanets, we often had to assume the atmosphere was uniform, a single, unchanging model. But Webb is sensitive enough to see that the atmosphere is not the same everywhere. The morning terminator, where the planet rotates from night into day, looks different from the evening terminator, where it rotates from day into night. On the morning side, the wind is coming from the cold night. It is cooler. The clouds might be thicker there, having had time to condense in the darkness. As this air crosses into the day side, the star blasts it with heat. The clouds might rapidly burn off, evaporating like morning mist under a hot sun. On the evening side, the air has been baking in the heat all day. It is hot, perhaps clear of clouds, loaded with rock vapor. As it crosses into the night, it begins to cool and the cloud formation begins again. This asymmetry, the difference between the morning and the evening, is the fingerprint of weather. It is the signature of a dynamic, moving system. It tells us that the planet has a morning weather forecast and an evening weather forecast. Cloudy with a chance of liquid iron rain in the west, clearing up with scorching heat in the east. It is easy to get lost in the data, in the graphs and the spectra. But we must remember what these numbers represent. They represent a physical reality. Somewhere, right now, in the velvet black of the galaxy, there is a world where the sky is filled with clouds of glass. The winds there are howling with a ferocity that would strip the flesh from bone. The heat is enough to melt lead. It is a hellscape by human standards, and yet there is a profound elegance to it. The laws of physics are playing out their symphony on a grand scale. The same forces that shape a snowflake in a winter storm on Earth are shaping a crystal of forsterite in the upper atmosphere of this distant giant. The James Webb Space Telescope has allowed us to bridge the gap between the abstract and the tangible. We are no longer just calculating the mass and radius of these worlds. We are sensing their texture. We are feeling the grit of their air. This discovery challenges our definition of weather. We tend to think of weather as a biological necessity. Rain brings life, sun brings growth. But weather is older than life. It is the universe's way of moving energy. It is the thermal breathing of a planet. And this planet is breathing. Deep, slow, rhythmic breaths of hot gas and silicate dust circulating endlessly in the void. As we continue to observe, we will likely find even more complexity. We may find layers of clouds made of different materials, perhaps clouds of iron vapor below the silicates or clouds of salt. We may find storms that last for centuries, like Jupiter's Great Red Spot. We may find that the weather changes over years, indicating seasons driven by subtle wobbles in the planet's orbit. The detection of silicate clouds is just the first drop in a deluge of knowledge. We have opened a door. We have stepped through the threshold of discovery and found ourselves standing in a rain of diamonds, looking up at a foreign sun, realizing that the universe is far more dynamic, far more textured, and far more active than we ever dared to dream. The silence of the stars is a deception. Up close, the universe is roaring. We have floated through the alien winds, felt the searing heat of the eternal day, and watched the condensation of rock into clouds of glittering dust. But how do we know any of this is real? The planet is not a place we can visit. It is light years away, a speck of darkness orbiting a blinding star. We cannot send a probe to taste the air or release a weather balloon to measure the pressure. We are bound to Earth, or at least to the vicinity of Earth, looking out across the vast, empty gulf of space. The answer lies in the rainbow. It lies in the spectrum of light that the James Webb Space Telescope collects. This is the language of the universe, and learning to read it is one of the greatest achievements of human intellect. Imagine a single beam of light traveling from that distant star. It carries within it the history of its journey. As it passes through the outer layers of the star, atoms of hydrogen and helium absorb specific colors, leaving dark lines in the spectrum, the stellar fingerprint. Then, the light travels through the vacuum of space, untouched for centuries. Finally, it reaches the planet. Some of the light hits the atmosphere. It skims the cloud tops, it filters through the haze, and in that brief interaction, the light changes. The atmosphere is a soup of molecules. Each molecule is like a tiny tuning fork. It vibrates at a specific frequency. When light of that exact frequency hits the molecule, the energy is absorbed. The light disappears from the beam. Water vapor absorbs infrared light at specific wavelengths. Carbon dioxide absorbs at others. Methane, ammonia, carbon monoxide. They all have their own unique barcodes. By spreading the light out into a spectrum and looking for these missing bands, astronomers can determine exactly what the atmosphere is made of. But the James Webb Space Telescope did something even more subtle. It didn't just look for static fingerprints. It looked for changes in the fingerprints. As the planet rotated, different parts of its atmosphere came into view. The telescope watched as the morning side rotated into view, then the noon side, then the evening side. It collected a continuous stream of light, building a map of the planet's atmosphere slice by slice. This is called phase-resolved spectroscopy. It is like watching a spinning globe and taking a spectrum of each continent as it passes by. The data revealed a stunning complexity. On the night side of the planet, the signal for silicates, the rock clouds, was strong. The clouds were thick, blanketing the darkness, trapping the heat inside. But as the telescope looked toward the day side, the silicate signal weakened, the clouds were thinning out, the heat of the star was burning them away, turning the crystals back into vapor. This tells us that the weather on this world is driven by a cycle of cloud formation and destruction. It is a global engine. The night side acts as a cloud factory, churning out immense banks of silicate fog. The winds then carry these clouds toward the day side, where they are destroyed by the intense radiation. But the spectrum held another secret. It revealed the temperature structure of the atmosphere, how the temperature changes with altitude. On Earth, the air gets colder as you go up. That is why mountains are snowy. This is called a normal temperature profile. But on some exoplanets, the opposite happens. The air gets hotter as you go up. This is called a temperature inversion. It happens when there is something in the upper atmosphere that is very good at absorbing starlight. On Earth, the ozone layer does this, absorbing ultraviolet light and heating up the stratosphere. On Jupiter, complex hazes do it. The data from Webb suggests that this distant world has a similar structure. The silicate clouds themselves might be acting as a heating layer. They absorb the starlight, warming the upper atmosphere and creating a lid of hot air that traps the weather below. This inversion layer is crucial. It stabilizes the atmosphere. It prevents the deep, hot air from rising too quickly. It creates distinct layers of weather, just like the layers of an onion. In the lower atmosphere, deep below the clouds, the winds might be sluggish. The air is dense, crushing, and hot. In the middle layer, where the clouds form, the winds pick up speed. This is the weather layer, the turbulent zone of mixing and condensing, and above the clouds in the thin upper atmosphere, the winds scream around the planet in the super-rotating jet stream we discussed earlier. By peeling back these layers with spectroscopy, we are effectively doing a CT scan of a planet light years away. We are seeing its internal structure, we are seeing the machinery that drives the climate. And this machinery is remarkably similar to what we see in our own solar system despite the alien ingredients. The physics of fluids, of heat, of rotation, they are universal. A storm on Earth, a storm on Jupiter, and a storm on this exoplanet are all governed by the same equations. The only difference is the variables, the temperature, the gravity, the chemical composition. This realization is profound. It means that the universe is understandable. It is not a chaos of random events. It is a system ordered by laws. And by studying the extreme weather of these distant worlds, we are testing those laws to their breaking point. We are learning how atmospheres behave under conditions that are impossible to replicate in a lab. We are learning that weather is not just rain and sunshine. It is a fundamental property of any atmosphere. It is the inevitable result of energy flowing through gas. Wherever there is air and heat, there will be wind. Wherever there is a temperature difference, there will be a storm. The James Webb Space Telescope has turned the study of exoplanets from a game of detection into a science of meteorology. We are no longer asking, is there a planet there? We are asking, what is the weather like there? And the answer for this world is cloudy, with strong winds from the west and a high chance of silicate rain. As we conclude this journey, let us pull back from the swirling winds and the glittering clouds. Let us retreat from the intense heat of the alien sun and drift once more into the cool, quiet darkness of interstellar space. The planet we have explored is just one point of light in a galaxy of hundreds of billions of stars. It is a single grain of sand on the cosmic beach. But it is a grain of sand that has spoken to us. It has told us its story. The discovery of active weather on a distant world is a milestone in human history. It marks the moment when the universe truly came alive for us. For millennia, the stars were distant gods, then they were distant fires. Now, they are places. They are destinations. They are worlds with their own skies, their own storms, their own cycles of day and night. The James Webb Space Telescope is our bridge to these worlds. It is a testament to our curiosity, to our need to know what lies beyond the horizon. It is a machine built by thousands of hands, launched on a pillar of fire and unfolded like a golden flower in the void, all so that we could see the invisible. We have seen the wind, We have seen the clouds. We have seen the dynamic, ever-changing nature of a planet that no human will ever set foot on. And this is just the beginning. There are billions of other worlds out there waiting to be discovered. Some will be like this, one-hot giants with clouds of rock and iron. Others will be ice giants, shrouded in blue methane mists. Some will be rocky worlds like our own, perhaps with oceans of water, perhaps with clouds of simple water vapor, perhaps even with the chemical signatures of life. The techniques we have honed on this hot Jupiter, the phase curves, the spectroscopy, the modeling of winds, are the same techniques we will use to find the second Earth. We are practicing on the giants so that we can one day understand the small, rocky worlds where life might cling to existence. Every observation brings us closer to that ultimate goal. Every spectrum is a piece of the puzzle. Every weather report from a distant star adds to our understanding of the cosmic climate. But even if we never find another Earth, the discovery of weather on this alien world is valuable in itself. It reminds us of the sheer diversity of the cosmos. It reminds us that nature is not limited by our imagination. It can create clouds of sand, it can create winds of fire, it can create worlds that are both terrifying and beautiful in their extremity. It invites us to look up at the night sky with a new sense of wonder. When you see a star twinkling in the darkness, remember that it is not just a point of light, it is a sun. And orbiting that sun may be a world where a storm is raging right now. A world where the wind is howling through a sky we can scarcely imagine. A world where the universe is expressing itself in a language of heat and motion. The silence of space is an illusion. The universe is breathing, it is churning, it is alive with energy. We are the listeners. We are the watchers. We are the species that built a golden eye to see the weather on the other side of the galaxy. And as we continue to watch, as we continue to listen, who knows what other wonders we will find in the deep, dark ocean of the stars. The wind is blowing out there. The clouds are drifting. The universe is waiting. The story of the James Webb Space Telescope and the weather on distant worlds does not end with the detection of silicate clouds. In science, every answer is a seed for a new forest of questions. We have established that exoplanets are dynamic. We have proven that we can see their storms. But the natural progression of our curiosity leads us to a deeper, more profound question. If we can see the weather, can we see the life that might live beneath it? The detection of weather is the dress rehearsal for the detection of biology. The techniques used to find the shifting winds on a hot gas giant are the exact same techniques, refined and pushed to their absolute limits, that will be used to find the breathing of a living biosphere. Consider what weather actually is. It is the movement of energy and matter. Life, in its most basic definition, is also a movement of energy and matter. It takes in nutrients, processes them, and expels waste. On a planetary scale, the collective breathing of a biosphere changes the atmosphere. It creates a chemical disequilibrium. On Earth, plants consume carbon dioxide and release oxygen. Animals consume oxygen and release carbon dioxide. Bacteria produce methane. If an alien astronomer were looking at Earth from light years away, they would see oxygen and methane existing together in our atmosphere. This is strange because oxygen and methane react with each other. They shouldn't coexist for long unless something is constantly replenishing them. That something is life. The James Webb Space Telescope is currently hunting for these signs on smaller, cooler worlds. It is looking at planets in the TRAPPIST-1 system, a family of 7 rocky worlds orbiting a red dwarf star. These planets are Earth-sized. Some are in the habitable zone, where water could exist as a liquid. But seeing the atmosphere of a rocky planet is infinitely harder than seeing the atmosphere of a gas giant. The atmosphere is thinner, the planet is smaller, the signal is fainter. It is like trying to see the fuzz on a peach from 10 miles away, whereas the gas giant was like seeing the peach itself. However, the discovery of weather on the hot giant gives us hope. It proves that our models of atmospheric circulation are working. It proves that we can distinguish between clear skies and cloudy skies. This is vital. If we look at a rocky planet and see a flat line in the spectrum, it might mean the planet has no atmosphere, a dead rock. Or it might mean the planet is covered in a thick, high-altitude layer of clouds that blocks our view of the gases below. Understanding the weather of clouds, how they form, what they are made of, how they move, is the key to unlocking the secrets of the rocky worlds. If we can model the clouds, we can subtract them from the data. We can peel back the veil and see the chemical fingerprints hidden underneath. We are currently in a transition phase. We are moving from the era of exoplanet botany, cataloging the types of planets, to exoplanet biology. We are looking for the metabolic hum of a planet. James Webb is the pioneer. It is the scout. It is finding the targets, characterizing the atmospheres, and telling us which worlds are the most promising. But it is also paving the way for the next generation of giants. The Habitable Worlds Observatory, a concept for a future telescope, will be designed specifically to image Earth-like planets directly, to see them as pale blue dots rather than just shadows crossing a star. But without the groundwork laid by Webb, without the understanding of silicate clouds, superrotation, and atmospheric dynamics, we would not know where to look or how to interpret what we see. The weather we found on the hot giant is a reminder that the universe is not static. It is evolving. And somewhere, perhaps on a world with gentler winds and softer clouds, that evolution has taken a step beyond chemistry and into the realm of biology. The wind there might not be carrying sand, it might be carrying pollen, it might be carrying the spores of a life form we cannot yet imagine. We are listening to the static of the universe, and we have heard the thunder. Now, we are waiting to hear the whisper of a living world. History is often measured in eras defined by tools: the Stone Age, the Bronze Age, the Iron Age. In the timeline of astronomy, we have entered the Gold Age, the era of the golden mirrors. The James Webb Space Telescope will not last forever. It has a finite supply of fuel to maintain its orbit at Lagrange point 2. It has a finite lifespan before its electronics degrade in the harsh radiation of deep space. Like the great cathedrals of old, it is a monument built by mortals, destined to eventually fall silent. But the light it collects is immortal. The data gathered from the distant world with the silicate clouds is now stored in the archives of humanity. It is a digital artifact, a snapshot of the universe as it existed at this moment in time. Centuries from now, long after the telescope has drifted away or been decommissioned, astronomers will still be looking at this data. They will look at it with new eyes. They will use algorithms we haven't invented yet. They will have theories we haven't dreamed of. They might find secrets in the noise that we missed. They might see patterns in the weather that we interpreted as chaos. This is the true legacy of the mission. It is not just the immediate discovery of wind or rain. It is the creation of a library of light. We are archiving the sky. And what a sky it is! We have moved from a universe of points and lights to a universe of places and processes. We have realized that the galaxy is a collection of environments. Some are hellish, some are frozen, some are chaotic, and some are serene. The detection of weather on a distant world changes our psychological relationship with the night sky. When you look up now, you are not looking at a painting, you are looking at a window. Through that window, if you could see far enough and clear enough, you would see storms raging. You would see sunrises that melt mountains. You would see sunsets that freeze oceans. We are no longer alone in a cold, empty void. We are neighbors in a crowded, noisy, windy galaxy. The distance between us and them is vast, yes, but the light bridges that gap. The wind bridges that gap. The story of the universe is the story of matter trying to understand itself. The hydrogen atoms in the early universe coalesced into stars which forged heavier elements, which formed planets, which eventually formed us. And now, we organized collections of atoms are building machines to look back at the stars and understand where we came from. We are the universe waking up. We are the universe checking the weather. As the James Webb Space Telescope continues its silent vigil, turning its golden eye from one target to the next, we can rest assured that the age of discovery is far from over. The clouds of the hot giant were just the opening act. The curtain has just risen. The show is about to begin.